Hello and welcome. My name is Flower Grills, and welcome back to my series on covering the entire Ableton Live manual through tutorials. So here we are back in Ableton, and I've made this little beat. Which is, again, totally irrelevant to the video. But today we're going to cover audio settings. This is a very important part of the settings, probably one of the most important. Now, as you can see here, this is 2.3.3 in the live manual. There actually isn't very much on the settings themselves in the manual. It actually suggests going through the audio input and output lesson inside of live. I'm going to take you through that lesson. So the way you can get to it is if you go to help up here, then go to built-in lessons. And then as you can see here, these are all a bunch of very useful lessons for live. There's audio input / output. So you press there and then we can follow these settings. In this lesson, we'll set up and optimize live's audio input and output settings. It will take about 10 minutes to configure everything, but this process only needs to be done once for each audio interface you use. So let me open up the settings on the side here so you can have a view of them. When we're finished, we'll have accomplished the following things: selecting a driver type, here, choosing input and output devices, here, configuring ins and outs, these are the channel configuration right here, selecting the sampling rate, so this is this section, and then adjusting the audio input and output buffer size, this is this, and then it doesn't mention, but it's also, there's the test tone, which you can use to test the latency and sample rate settings there. So as you can see here, I'm going to move to the next page. The audio input output settings are found in Live's audio preferences. Again, it depends on your system. It might be called preferences or settings. You can get to them by going to Live up here and then pressing settings, or you can see the shortcut here as well. On Mac, it's command, comma, and it'll come up. I'm going to press next page again. The audio device settings refer to physical audio interfaces which are either built into your computer or connected to it externally. Live communicates with audio devices through a piece of software known as a driver. Essentially, on MacBook, there is Core Audio. This is a software which communicates between the digital audio workstations such as Ableton and external hardware. And every system needs this, and on Windows there is ASIO. Once you've selected a driver type here, you'll be able to specify inputs and outputs using the audio input device and audio output device choosers. So you can see here, I've selected Core Audio. If I select No Audio, then this message down here shows the audio engine is off. Please click here to choose an audio device from Live's audio settings. So you need to pick a driver type, and now you can select an audio input device and an audio output device. If I wanted to record my microphone right now, I would actually pick the Scarlett Solo USB. This is my audio interface. It's a Focusrite Scarlett. So I could press here. And then if we go to over here, you can see that there is signal coming into Live from my interface. Whereas if I go to the No device, it disappears. If I go to my MacBook Pro microphone, then it will pick up not my microphone that I'm using right now to record this video, but my MacBook microphone. So if I tap that, you can see it go in the red. We can leave it like that for now because I'm not going to use it. And audio output device. So on MacBook, there's the option to use system device. This makes it easier. So anytime you open up Live and say one time you're producing just with your headphones, another time you're using an interface, you can use this option and it will select whichever option selected in the MacBook preferences. I find that quite useful. So I keep it on use system device, and as my system already automatically connected to my Scarlett interface, I'm also using the Scarlett Solo USB for my audio output device in Live. So what comes up in these two lists here is entirely dependent on your setup. For example, here I've got Pro Tools because I've once had Pro Tools on this MacBook. I have Microsoft Teams Audio because I have Teams installed. And Black Hole is something used to record audio, screen audio. So these are all very specific things from my setup, and it will entirely depend on your setup. It might have just 3 options, for example, or many more. Now you can also see a note here that Core Audio allows 2 different devices to be used for input and output. We recommend selecting the same device for both in order to avoid potential conflicts. So next we have the channel configuration here. If we go to press the input config button, it will open this. These are on-off switches right here. If you press it off, it will say, warning, this change will disable active track routings. To view and modify track routings, choose in/out from the view menu. I don't have an interface with multiple inputs or multiple outputs. My Scarlett Solo interface only has 2 inputs. As you can see here, it says 2 in/2 out, and you can choose to either have it in stereo or mono. If you know it's always going to be stereo, you can turn off mono. Or if you know it's always going to be mono, if it's a mono microphone, you can turn off the stereo, and that will save CPU usage as well. Now, if you have an interface that has many different inputs or outputs, you can also name them here. That's what these little black bars are for. Let's say we name our mono input for my interface AKG mic, because that's what I'm using. If we go back to live now, you can see it actually shows up as AKG mic. So that's quite useful. That's pretty good for organization, especially if you have more than one input. So there you go. That's how you can set up an audio interface, and also, very importantly, set up your driver. Now, to help explain some of these concepts here, I'm not going to get too much into science, but it's a little bit important to help you understand these concepts for the future. So, what is sound? Sound is a sinusoidal change in air pressure caused by a simple vibration back and forth. And you can visualize that change in air pressure as a sine wave going up and down. This is pressure, the y-axis, and this is time. So you can even see it looks like a vibration on this graph. Now, we have to understand the basics of digital representation of sound in order to understand sample rate and buffer size. So consider how a film represents motion. If you've ever worked with editing or films, you will know that a film uses a frame rate. And one of the most common ones is 24 frames per second, because it's the minimum amount of frames needed to actually produce a moving image, something that tricks our eyes into believing that it's moving, that it's fluid. And then, of course, if you're into gaming, you'll understand that 60 frames per second feels much smoother than 30 frames per second in a video game, because there are more frames per second, there are more images that you perceive, and then it will look smoother to your eyes. So the job of a microphone, for example, is to transduce or convert one form of energy into another, the change in air pressure into an analogous change in electrical voltage. This continuously changing voltage can then be sampled periodically by a process known as sample and hold. So this is what it ends up looking like, right? Here, the microphone in certain time segments is being told to hold a voltage. Now, in order for a computer to represent sound accurately, many samples must be taken per second, many more than are necessary for filming or visual image. As I've just said, 24 frames per second is actually all you need to create the illusion of moving image. Now, considering that visual files take up much more storage space on a computer than audio, it still takes a lot of storage space and a lot of computing power to process, and that's why editing is still intensive for a CPU. Audio needs many more samples in order to represent a wave accurately. Now, here's a graph to help you understand what humans are capable of hearing. So, as you can see here, this is lower frequency, this is higher frequency. A human is capable of hearing from 20 hertz to 20,000 hertz, just about. As you can see, there's certain animals that can hear actually a lot higher, like bats, 1,000 to 120,000 hertz. And there's also some animals such as elephants, which can hear a lot lower, like 5 hertz to 12,000 hertz. We're not capable of hearing something that's just 5 hertz. So when making music, we need to represent waves accurately within this range, within 20 to 20,000 hertz, so that we can hear it. Here's a useful video that I'm going to link in the video description. So if we have a sine wave here, and we have a sampling frequency of 7 hertz, or 7 samples per second, it's going to look like that. This is what it's going to look like for the computer in terms of this sound wave. So then it's going to have to interpret and understand, well, what was the original audio? And now, are there any other sinusoids that will have these exact same values? And actually, yes, there would be many, right? If you go up, then in certain intervals, there are going to be many, many frequencies that will have the same samples taken out of the 7 hertz. So this means that if we take the lowest possible wave, then that is likely to be the correct one. But see, if you have a sampling frequency of 1.5 hertz, these are the dots that you take. So these are the samples, 1, 2, 3, 4. But we're taking a sample 1.5 times per second. So now, which waves are possible? Well, it's actually not just intervals above this wave. It's waves that are lower than this wave, as you can see here. And so if we now have decided, well, we're always going to take the lowest wave possible, and that's the correct one, now this doesn't work. So that's what the Nyquist-Shannon sampling theorem is. That basically you have to have a sampling frequency twice as big as the waveform or the signal in order to accurately represent it or find it. So if we have 16,000 samples of an audio signal per second, we can only capture frequencies up to 8,000 hertz without aliasing. Now, aliasing, what it means is that it's similar to a fold over, that because of that fancy maths that's going on, at some point, these lower waves are going to be identical to that actual original signal. And at that point, when we're trying to represent these high frequencies, maybe 15,000 hertz, it's actually going to be identical to the computer to something that's maybe 2,000 hertz. So it's going to create these low sounding and incorrect sounds, making the audio just not accurate to how it actually sounded. So it says here, the main problem with aliasing is that it can add frequencies to the digitalized sound that were not present in the original sound. And unless we know the exact spectrum of the original sound, there is no way to know which frequencies truly belong in the digitized sound and which are the result of aliasing. So this is why most people use the 44,100 sample rate. This, if you divide it, you get the Nyquist frequency, which is 22,050. So that is just above the range of human hearing, as we saw here, right? 20 to 20,000 hertz. So if you have 44,000 hertz, that's twice than the range of human hearing. So you'll be able to accurately represent sounds within the human hearing range. I have it just a bit higher. It doesn't make that much of a difference, but I liked 48,000 hertz. So if you have an insane sample rate of 192,000, then you'll be able to accurately represent half of that, which is 96,000. So you wouldn't need that. Not really anything above 44,100 hertz you would need, but that's what the sample rate is. It's similar to frames in video. It's how many samples you're taking of a waveform in order to accurately represent it. And so, for example, if you're recording something into Ableton through a microphone, you're turning an analog sound of that air pressure into voltage, but how many snapshots of that voltage are you taking to accurately represent the altitude of the waveform? And that's exactly what that is. So right now, I would be taking 48,000 samples per second, which is a lot, but that's what's needed to have twice of the Nyquist frequency. Hello, I forgot to mention this, right? That your sound interface, your audio interface, is likely to have some sort of control app. And this is very important to figure out what the sample rate is of your audio interface. For me, I got this on the internet. I went to this Focusrite website, and then I found my one, which was here, Scarlett Solo. And then I downloaded this software. This software lets me remotely control my audio interface. So it's literally changing the settings on the hardware. But also, if you press the preferences here, you can see the sample rate. Now, this is very important. If I were to change this to 44.1 kilohertz, but kept 48 in Ableton, that would introduce huge problems. So it's important to remember that your audio interface and your DAW, in this case live, have to have the same sample rate. So next here we have the default SR and pitch conversion. What that means is default SR, default sample rate, and pitch conversion. You can set it as normal or high quality. So for example, it says here in info view, if you look at the bottom left, if the switch is on, high quality sample interpolation will be activated for new clips by default. If you listen to this drum sound here, right, as you can see here, this is the switch that it's talking about. So because I have it on in the preferences, it will always be turned on in every clip of sound that I have. So what it means, it's using a more sophisticated interpolation algorithm. Interpolation is if you have this audio wave here, if you look right in there, remember the sample rate and how many samples we have to represent a sound. Well, how do you go smoothly between these samples? That's what interpolation is, and a more sophisticated algorithm means it's going to more accurately and smoothly move between those samples. And it also affects pitch shifting. So it says here pitch shifting will then create less distortion at the expense of higher CPU drain, and we can actually represent that. So if I go to -48 and then I press play, this is with the high quality on. If I turn it off, you can hear a lot of distortion, especially in that higher end frequency sound. So that is what the default SR and pitch conversion setting does. Next, we have latency. So first we have buffer size here. It says here in the tutorial that all audio passing through your computer is stored momentarily in buffers, little sound reservoirs which keep the audio stream flowing when your CPU needs to pay attention to other tasks. Large buffers ensure an uninterrupted flow of audio at the expense of a sluggish response in the software. Small buffers provide a snappier response but are more likely to run dry, interrupting or mangling your sound. So what that means, if we have, for example, a 32 samples buffer size, live is going to wait 32 samples out of that 48,000 sample per second sample rate before playing audio. And maybe you've guessed it, but that's what latency is in this case. In this case, input latency. The pure input latency, of course, I have a higher latency here because of my audio interface, but the pure latency would be the buffer size divided by the sample rate. So if we do 512 divided by 48,000, and remember this is in seconds, so it actually would be 10 milliseconds, 0.66, so we can say 11 milliseconds. And that's pretty close. 11 milliseconds is not far from 13.9, so it means that my audio interface is adding about 2 milliseconds to the latency. Now, before we move on to latency, let's quickly jump down to this test section, because this is actually what you can use to determine a good buffer size. Now, if you turn the test tone on, you can see here my CPU usage in the top right jumps up. It's at 42%. Well, why? That's because of this setting here, the CPU usage simulator. So this is going to simulate CPU usage. If I turn it to all the way to 80, you can see it go up to 80 here as well. So this is what it's actually recommending. You can go down to 48, and then, well, just until you're able to hear it, and then you can go to different buffer sizes to determine where you stop hearing crackles and distortions. So this is what 32 samples sounds like, right? This is I mean, in some way, in terms of noise music, maybe quite beautiful, but I don't think it's what you want when you're trying to accurately represent just this sine wave, right? Let's move to 64. As you can see, it's starting to sound like that sound wave. And because we are simulating that 80% CPU usage, the CPU is being strained by having such a small buffer size, right? So it has to instantly play the tone. It's just, at this point, as you can see here, the latency, it's very small. Let's go to 128. Now it's starting to sound like the original. Now, I know from my experience that I like 512, especially when I'm not recording audio or anything like that. 512 is actually better for plugins and things like that, because it lowers the CPU usage of having a small buffer size. So it depends what you're using, I would say. If you're, I'll turn the test tone off. If you're focused on recording instruments, you can lower the buffer size and be careful of not straining your CPU too much. But if you're just focused on producing and exploring CPU intensive plugins, maybe try increasing the buffer size to make it easier on your live software. So that's the test tone, and how you can use that section to find your correct buffer size. What about this latency, input latency and output latency? The input latency is the latency, for example, from this microphone. If I were to record singing into live, it would take 13.9 milliseconds before it would show up in live. Now, there's another bunch of tutorials here on driver error compensation, and that's actually really useful for understanding latency. This lesson is accompanied by a live set, so you can click in that lesson again. You can find the lesson by going to help, and then built-in lessons, and then on the last slide of the audio input and output, you can go to driver error compensation, and you can press here to load the correct live set. So here we are. I'm taking input from my AKG mic, which is connected to my Scarlett audio interface. So again, if we open settings by Command, comma, I can actually change that for a second, go to MacBook Pro microphone, and the audio output device, I'm going to put the MacBook Pro speakers just for this demonstration. So you can see here that my MacBook is creating the sound. So here's the sound, and you can see exactly here how much delay there is, how much latency there is based on how much later this gray little volume is reacting to the actual volume playing from the speaker. So if you watch again, you can see there's quite a delay. Now if we record it, you can see the delay here. Do you hear how far back this was, right? So what this is suggesting is that once you recorded it, you can turn off warp. I've already done that. And then you can use this little start point here to offset the wave to make it match exactly the first wave. So again, remember to turn off warp and then zoom in. And now you can move the waveform literally by milliseconds. This is milliseconds right here. Move it to the left. And then you can make it match. I would say there's matches. I could be wrong, but if I play it back. Now that we have this value here, which is 59 milliseconds, that is what you can put into driver error compensation. So you can put 59, and now we can go back, and now I've recorded it again with that driver error compensation here being 59, which is what we determined just now, right, by moving this clip to the start point of this clip. And as you can see, it recorded perfectly in line. So that's how you can determine the driver error compensation. And what that means is, as you can see in the bottom here, some audio interfaces report incorrect latencies. With this setting, you can tell Live about any deviation that it can detect on its own. So if you remember the driver from the beginning, right, when we chose the driver type, which on MacBook is Core Audio and on Windows could be ASIO, that driver is a piece of software and it's telling the MacBook how much latency there is at any given point because of the hardware. But the driver makes errors. And to compensate for that error, you can put that in here. And then what is the overall latency? So the overall latency is the all the way round trip from when you record something into Ableton, say with a microphone or with a MIDI keyboard, and then Ableton processes it and puts it out of your speakers. So mathematically, what would that be? It would be 5.33 milliseconds for me, plus the output latency, 7.33 milliseconds, plus the driver error compensation, which I have just figured out using our experiment here, right? So if you add those three together, 5.33 plus 7.33 plus 59 milliseconds, here's the answer, 71.66. And that matches 71.7 milliseconds. So that's the overall latency, which means the round trip of the audio if you use a microphone and it goes back out the speakers. So I hope that makes sense. As you can see, it's essentially a formula here because to get the input latency, you divide the buffer size by the in-out sample rate. To get the output latency, that's something that you can't control, but Ableton just determines that using the driver. You can actually see a change. So right now it's a lot lower because I'm not using the audio interface. As you can see here, I'm using the MacBook Pro mic and the MacBook Pro speakers. If I change it back to my Scarlett audio interface, you can see it jump up here, which in this case, because of the Scarlett, surprisingly, it's lower than the input latency. That can happen. And then we have the driver error compensation, which we have determined ourselves. And then we have the overall latency, which is this number plus this number plus this number together. So I know this is all very confusing, and these settings have confused me for years. But all you really have to remember is the sample rate. This is the absolutely fine setting. And if you want to have a tiny bit more, 48,000 is fine as well. Anything above that you don't really need. I would keep the buffer size above 256, but it depends on the project you're working on. With the driver error compensation, you can go through the tutorial to figure it out, what is yours, and then that will stay the same in the settings. It will be saved, but it will only be specific to this hardware setup, right? So because I just changed it to the Scarlett, this doesn't apply anymore. I would have to do that experiment again and figure it out. So this only applies to the MacBook Pro microphone and the MacBook Pro speakers. Now the overall latency is correct. So yeah, I would say anytime you're changing your hardware setup, if you're using headphones and the laptop mic or a MIDI keyboard, or if you're using a new interface or something like that, I would always have a look at the latency settings. And if you have a new MacBook, a new laptop, or an old one, or you're working on someone else's laptop, then it's also good to have a look at using this test section and determining what buffer size works best, and also the sample rate settings here, so that you can have the lowest idle CPU number possible. So that's it for this video. I know it's a longer one, but the audio settings needed a lot of explanation. I hope it helped at least a little bit. The MIDI settings are next, and they're just as complicated, unfortunately, but I hope I could help you understand a bit better, and I'll see you in the next one.